Good morning, children. So, in the previous class, we dealt with covalent bond after ionic bond. And we have also seen that in covalent bond, the atoms which are taking part or participating in the bond share their electrons, but their electrons will not get transferred to the another atom. And now coming to bond length or the bond distance in case of covalent bonds. So it is something like where it's only like sharing of electrons, right? So it is not something like that. The transfer of electrons is not taking place. It is not an electrostatic force of attraction so that they both come closer and then stick to each other. So according to whatever the electron valence theory is there, so how the covalent bond is defined only like each atom whichever is participating in covalent bond contributes one electron for sharing only. That means these shared electrons belong to all the atoms, right? So both the atoms, in fact it is to both the atoms. Now if that is the case, there would be some distance between the nuclei of the atoms which are taking part in the bond, and that distance between the nuclei of two atoms what we call as a bond length. So distance between the nuclei of the atoms which are participating in covalent bond, that is called bond length or bond distance. Bond length or bond distance. Usually the units are in nanometers. Nanometer means 10 power minus 9 meter, or measured in angstroms. Angstrom is the most common unit in chemistry. Usually whenever you solve problems in chemistry, it is angstrom is the most common unit, where 1 angstrom is written like that, 1 power like 0, it's a degree kind, and is equal to 10 power minus 10 meters. 1 angstrom is equal to 10 power minus 10 meters. Next word is bond energy or bond dissociation energy. So what is this dissociation energy? Energy needed to break a covalent bond. Between what? Covalent bond between two atoms. Then we call it as diatomic covalent bond. So when energy needed to break a covalent bond, how much energy we have to supply in order to break a bond between two atoms, that energy we call as bond energy or bond dissociation energy. So what is that called? Bond energy or bond dissociation energy. That is the energy needed to break a covalent bond between two atoms, or in short we can say that to break a diatomic covalent bond. Okay, children. So we have now discussed about so bond which is formed between two atoms by only sharing the electrons, but by and not by the transfer of electrons. That is a covalent bond. And there is a distance between the nuclei of the molecule which is formed because of the covalent bond. That is called the bond length or the bond distance. And when compared to ionic bond, covalent bond is a little bit weaker. Ionic bond is much stronger, and the energy needed to break a covalent bond is bond energy or bond dissociation energy. Right. So now let us check whether this whatever the valence theory, electronic valence theory, whatever is proposed before by Lewis and Kossel, is it free of defects? No. There are few drawbacks. Of electronic theory of valence. So already this we have discussed. Who proposed it? Lewis and Kossel. Right? So based on what? Based on valence electrons. Like that is what Lewis dot structure also is about. And then from valence electrons they said that which are the particular atom elements in the periodic table which do not chemically react with any other, that we called as inert gases. Why? Because they satisfy the octet rule. This is also proposed by electronic theory of valence. And now when we have seen, like means when people have studied this electronic theory of valence, and then they understood ionic and covalent bonds and all that. So specifically when it comes to the molecular shapes, this theory could not like explain the shapes. That is one of the drawbacks. And then also, see, when we define bond length or bond energy, we are saying that each atom will be contributing one electron, and means one covalent bond is formed between two electrons, is it not? So there is no kind of any difference in the covalent bonds that are formed. Then, as per this theory, all the covalent bonds, like lengths, should be same. Is it not? Because covalent bond is between the atoms, which will contribute each electron, and then those two electrons belong to both the atoms, and they are under attraction of both the nuclei. That means it is only bond which is because of two electrons being combined together. So there should not be any difference in bond length or bond energy as per this theory. But practically we observed that bond lengths and bond angles are not same whenever there are different atoms participating in the bond. Right? Whenever there are different atoms participating in this, that means there are different angles and different bond lengths for different particular atoms which are taking part or participating in covalent bond. So that is one most important defect, that practically we could people could come to a conclusion that this theory cannot justify completely the behavior of the molecule or the structure of the molecule. That is, like, what is the angle between the bonds that are formed in a particular molecule. So like, suppose if you say the beryllium chloride molecule, if you take, so that means central atom being beryllium and on either side you have chlorine. An angle between the two bonds is 180 degrees. It could not explain why it is 180 degrees. And then similarly BF3, if you have three fluorine atoms and the central atom being boron, so here why it is 120 degrees, the angle between the covalent bonds is 120 degrees, it could not explain. Similarly, if you take CH4, that means bond between CH and CH covalent bond, so should is 109 degrees 28 minutes. This is also practically observed. So how is this so? That means methane, it is supposed to have four hydrogens at the four sides of a carbon atom. But here the angle seems to be 109 degrees 28 minutes. Why is it so? This theory could not explain. Similarly, suppose hydrogen-nitrogen covalent bond. In case of NH3, each the angle between the bonds is 107 degrees 18 minutes. And why is it that H2O, that means on the either side of oxygen there should be two hydrogens. That means it should be 180 degrees if we compare with beryllium chloride, because here you have Be and Cl2 on either side. Here oxygen and hydrogen on either side. If we say that if this can be explained very easily based on the theory, this should also have 180 degrees. But this is coming around 104 degree 31 minutes. And such things, such differences, why practically this kind of angle is observed, right, when bonds are formed with different elements or different atoms which are participating in covalent bond. So this theory failed in explaining the shapes of the molecules. So these two are the major drawbacks. That is, one is bond length and bond energies are not the same. And then shapes of the molecules were not explained by this theory. So these are the most two important drawbacks of valence theory, proposed by who and who? Lewis and Causal, right? Okay, children, then take the screenshot and copy the notes. So drawbacks of electronic theory of valence. And here angles. This is very, very important part. It could be asked in objective questions or also in 1 mark questions. Angle between the bonds in each molecule. So take a screenshot and copy this. And this theory, which failed like in explaining why the bond lengths and bond energies are different for different atoms, and which could not explain the structure of the molecule. As it failed, we have got another theory, the next one, that is valence shell electron pair repulsion theory. In short, it is called as VSEPRT, right? VSEPRT. So that is valence shell electron pair repulsion theory. So who proposed this? It's Sidgwick and Powell. Sidgwick and Powell, they both together proposed this valence shell electron pair repulsion theory, that is in short called as VSEPRT in the year 1940. And of course, any theory whichever we are proposing will be having some improvements in the later periods, like when people think in different directions and then when observe the different practical phenomena, something or the other new will be added or something will be corrected in every theory. So in likewise here also this theory is improved, further improved by Gillespie and Nyom, right? So Gillespie and Nyom in 1957 they improved it further. Right, so what does this theory do for us? So VSEPRT explains bond angles. Right, so how we have discussed just now, what are the bond angles formed in different molecules. So it is able to explain that one, as well as it is able to explain molecules of 3 or more than 3 atoms. So when there are 3 atoms or more than 3 atoms, what is happening and why is it so formed, right? And then forms covalent bonds with central atom, and also like, so these, like how these 3 or more than 3 atoms, how these are able to form covalent bonds with a particular central atom. So these are the points usually we discuss under valence shell electron pair repulsion theory. So the first drawback, that is the most important one of the drawbacks of the previous rule, is now explained here in this particular theory. Okay, so how is this explained? See, here according to this theory, whatever the electrons which are there in the outermost shell, so what we call them as valence shells, they do not behave as single electrons. They do not behave as single electrons. It is something like a cloud of electrons. All those electrons in the valence shell, they behave as cloud of charges. That means it's a charged cloud. See, when one charged cloud is coming nearer to another charged cloud, what happens? So that is also of similar charges. Then what happens? Repulsion takes place, is it not? Repulsion takes place. Here, similarly, suppose if in a valence shell you have these 7 electrons and this is forming as a cloud, and this also forms as an electron cloud. This is an also electron cloud. This is also an electron cloud. That means the charge of this and charge of this are similar. So thus what happens? So when instead of these atoms coming closer, they'll get repelled by this repulsion between these two clouds. Hence, molecules get specific shapes. So how many electrons are there? What is the intensity of the repulsion? And if they are getting repelled, how and where they will try to locate themselves or fix themselves. All these can be discussed based on this cloud theory, right? Hence, molecules get specific shapes. So, and then the next postulate or the next point of this is that, so total number of electron pairs and lone pairs in central atom usually are the one which are going to have some significant behavior in case of forming the angles. Like see, we have a central atom. So when this atom is contributing one electron and the other one is also contributing an electron, we have the bond pairs. These are what we call as bond pairs. And suppose if the central atom is also having lone pairs which are not participating in the bond, these electron pairs, that means one set is a bond pair and the other set is a lone pair. So these lone pairs and these bond pairs together will decide how the angle of the bond will be. Right. So how is that so? Third point gives us a clear explanation of that. Lone pairs occupy much space than bond pairs. Whichever lone pairs are there, so they occupy much space than these bond pairs. What they will do? So they will try to push these two, like push the bond pairs away from it, and they try to occupy more space. Right. So these lone pairs will occupy more space wherever they are. Like suppose if you take an water molecule, like whenever hydrogen is contributing one electron here and oxygen is contributing one electron here, two bond pairs are formed, and in oxygen you have two lone pairs also, but the central atom is having these together. Instead of forming 180 degrees here, they push these bond pairs away as they try to occupy more space. So lone pairs are occupying more space here. Because of that, the angles what we imagined theoretically are different from what we are able to observe practically. Right? So this is how we can explain like why there are different shapes and different angles in case of bonds. Okay, children. So pause the video for a moment. Take the screenshot. So we are discussing about valence shell electron pair repulsion theory. It is a shell electron pair repulsion. It's not electron repulsion, it is shell electron pair repulsion. Why? Because here the valence electrons in a shell behave as a cloud of electrons. So therefore the name here is shell electron pair repulsion. It is because of the repulsion what we expected is different from what practically we are observing. Take a screenshot. And the postulates. And try to write in statements in your own words. Now children, fourth postulate or the fourth point as proposed in this shell electron repulsion theory. If there are no lone pairs in the valence shell of central atom, then the atoms align with equal angles, or the bonds align. Rather we can say that bonds align with equal angles. See, now suppose let us see the example of beryllium chloride. What we have just seen, like what is the angle here? There it is 180 degrees. How to explain that? That we are coming here. See, what is the statement? If there are no lone pairs in valence shell of central atom. In central atom there are no lone pairs. But bond pair is formed. Thus only bonds are formed, isn't it? So beryllium being the central atom, chlorine. What is the valency of chlorine? 7. So each chlorine is having 7 electrons in its valence shell. Beryllium in the valence shell it is having 2 electrons. So here beryllium with 2 electrons from Lewis dot structure, chlorine with 7 electrons. So here these are the lone pair electrons. So they are paired already, and these are the one which are unpaired, and these form the bonds. So thus this is how the bond is formed. So beryllium is contributing 1 electron here, and chlorine is contributing, and a covalent bond is formed here. And here also beryllium is contributing 1 electron, this electron with this chlorine, this electron with this electron of the chlorine. So here So what is happening? These are the lone pair electrons not in the central atom. Please, here the point here is that when there are no lone pair electrons in the valence shell of central atom. Now if we observe the central atom, so whatever the pair of electrons which are around this particular atom are bond pair electrons. They are not lone pair electrons. So here there is a bond formed, here there is a bond formed, and the angle between them. That means here the bonds are like about 360 degrees. If it is divided by 2, we have 180 degrees. The angle between these two bonds is 180 degrees. So thus we can explain how the beryllium chloride is formed. Right, now let us see another example where you have 3 atoms around the central atom. So here boron is the central atom where 3 electrons are there in the valence shell, and fluorine. So fluorine 7 in the valence shell. So 3 fluorine atoms are combining with 1 boron atom to form 3 covalent bonds. How many bonds are formed? 3 covalent bonds are formed. And as per the statement here given, if there are no lone pairs in the central atom, the bonds are separated with equal distances. That is with equal angles. Right, so now see here you have all the 3. So one electron being bonded with one of the fluorine electrons. Here another with another fluorine electron, and another with the another fluorine electron. Now this is how the bond is formed. So here we don't have any lone pair of electrons around boron. Whatever we have are the bond pair electrons, but not lone pair electrons. So therefore there is no point that there is an electron cloud here repelling these. Hence they are at equal angles. So the angle between these two is 120, between these two is 120, between these two is 120. That means 360 is equally divided by all the 3. Right? So this is how the boron fluoride is formed, right? So therefore this is how the structure is. Understood, children, now? So this is very, very important. Please take the screenshot and copy the notes. Right, and with this today I'm going to stop, and tomorrow in the next class we are going to discuss methane. So in methane what we have? 4 hydrogen atoms at the 4 corners of carbon, at the 4 sides of the carbon. And what is the valency of carbon? 4 only. That means whatever the pair of electrons that are around carbon are only the bond pair electrons, but there are no lone pair electrons. If that is the case, as per the 4th point, whatever we have discussed till now, that they have to have aligned themselves with equal angles. That means their 360 divided by 4, that means the bond angle should be 90 degrees. But in just now we have seen in the table that it is not 90 degrees, but it is coming around 109 degrees 28 minutes or something like that. Why is it so? Why is not methane following the same rule as in case of beryllium chloride and boron fluoride? So here the 3 atoms are there, no lone pair of electrons, thus 360 is divided by 3 into 120 degrees bond angle. Here this is appropriately right, and it syncs with the 4th point. And here also beryllium chloride. So there are no lone pair of electrons around the central atom, and thus the angle is 180 degrees because only 2 bonds are formed here. But similarly in methane 4 bonds are formed, means bond angle should be 90 degrees, but that is not happening. Why is it so? That tomorrow let us discuss in the next class. Okay, so take a screenshot and copy the notes.